Now we're going to go from one random variable to multiple random variables. And for the scope of this lesson, we're just going to be looking at discrete random variables. Okay, so what do I mean by multiple random variables? Let me give you a real world example of this first. There is a great website called WebMD that is basically an example of a very large probabilistic model where you go in and you can put your symptoms and it's going to give you probabilities that you have different diseases or different outcomes. So if I say I'm a 30-year-old male and I have dizziness and a one-sided headache, it says, well, you probably have a migraine. It's possible you have something else like a stroke. Now, that was not a lot of information to put into this, so I would obviously want to put much more detailed information before trying to distinguish between migraine and stroke. But the idea behind this is I have a ton of different interacting random variables. I have random variables for all the different possible symptoms. I have random variables for all the different possible diseases. And together, this is one large joint probability model. Now, we're going to start with something not so hard as this. So let's go back to what we've thought about in the context of a single random variable. So far we've thought about just rolling, for example, a single die and modeling that random variable. Now let's add 2 to the picture. So I can now think of X and Y as the outcomes on my red and my blue die. And then I can define their joint probability. What's the probability that the red die lands on a 5 and the blue die lands on a 3? What's the probability the red die lands on a 2, the blue die lands on a 4? Together, all of these possible outcomes define what is called the joint probability mass function. Okay, so let's put this all together. For 2 discrete random variables, the joint probability mass function is a description of how the total probability is split over all the possible outcomes for X and Y. Notation, I'm going to be using this in this class. Key idea is your probabilities altogether, your joint probabilities must sum for 1, up to 1, because we account for every possible combination of X and Y. In general, if you just have a discrete joint distribution with just 2 random variables, so I'm going to just say discrete joint distribution of 2 random variables, because that's what I've shown as our example here, then I can do a table, I can do a histogram, and sometimes I can actually write it as a function. A closed form function is what we're calling. Not always possible. So table is most likely outcome in the sense, or most likely way of representing. And the way this works is just like when we were looking at joint probability tables when we looked at events. Now I'm saying, okay, the probability X is 1 and Y is 2, I'm going to put as this entry in the table right here. So there's a 1/8 probability of that joint X is 1 and Y is 2. Similarly, if I want to see that probability X is 2 and Y is 1, well, that has a 2/8 probability. So this is going to account for all possible values that X can take, all possible values that Y can take. So the sum of all of these values inside here have to be 1. Another way I can represent this, it's less useful, I would say, but it is something we can do, is with a histogram. Now this is a histogram of a different data set. These are not the same data set here, or not the same joint distribution, okay? But in general, I could imagine making a little grid and making the height of a little rectangle at a given point of the grid equal to the probability. And that's what's happening here. I have a grid, and the height of these rectangular boxes at each point represent the probability for that combination of variables. So in the middle of this picture, you can see how we're representing the joint probability mass function. And then on the sides, we've actually just represented individually the histogram for, say, the X random variable and the Y random variable. So that's just like projecting this data onto the side axes, or the side, in this case, planes, to get a visual of what these random variables look like on their own. And then sometimes you can write it as a closed form function. Sometimes you can't. I'd say in most practical applications you can't, But a lot of times we're going to try to do that with simplified models so that our life becomes much easier to handle, because we'll see how this becomes very hard to represent as we start adding more than just 2 random variables. So generally we're going to try to go for this as a simplified model form when we have more than just 2 random variables. But usually in the real world, the reality is I really could have maybe some interesting probability mass function that can't be summarized by a nice closed form function. Okay, let's go back to the dice just for our simplest example. So you roll 2 6-sided dice. They give you values x and y. Let's do the joint PMF. Take a minute and see if you can represent, try doing the table and the closed form function, and I'll do the histogram for us. Okay, the table's kind of a ridiculous question because all values in the table is 1 out of 36. I'm equally likely to get any combination of x and y because these are fair 6-sided dice. So I just stopped writing 1 out of 36, but that's basically the value for all of them. So now when I do the histogram, it seems kind of not as useful of information. These all have the exact same height because they all have the same probability. A lot of times when you have a situation like this, where you have these equal or uniform probabilities, then we'll actually represent it in a scatter plot. So imagine you're standing up here looking down at this, squashing it down, and we're just plotting this. And because this is telling me that these are all the values that x and y can take on, they all have equal probability for taking on these values. So the probability of any one of these points is 1 out of 36. Okay, I'm just highlighting these so you can see them bigger. There is a closed form function for this. It's just saying, the probability is always 1 out of 36 for all of my possible inputs. All right, so this is not that interesting of an example. In the real life, we often will have joint probabilities that have some variation, that are not uniform. So let's say we went out and surveyed every CU Boulder student and asked them for their year and their relationship status. This is made up data. We did not do this. But suppose we did, we could then put together this joint probability mass function describing how the random variable year relates to the random variable of relationship status. So reading the table here, the probability that if I randomly select a student at CU, probability that they're a junior and in a relationship is 10%. You notice that all of these, the sum of all these probabilities in the table have to add up to 1. And so ultimately, this joint probability mass function gives me complete information. Just using this table, I can answer any probability question I'm interested in regards to or related to these specific random variables. So for example, what's the probability somebody randomly sampled from this population is in a relationship? All right, well, if you notice, that means I want to take into account basically every probability in this column. I'm going to sum them up. It's going to give me 45% chance. And if you're thinking, wait, we've done this before, you're correct. This is really just using the law of total probability. We can do this again. I could ask you the probability a randomly selected student is a senior. And I could go this way along the table, calculate that sum. So actually using this joint probability mass function, I can also get the probabilities of the individual random variables. And those are called the marginal distributions. Mainly because, as you noticed, as I started to do that in the table, I was writing those summed out probabilities in the margins. That's where that name came from. So if you're thinking, well, wait, isn't this just the law of total probability? Yes. To get the total probability that x is equal to a, I'm summing. This is my law of total probability. And this is just the visual from when we covered it before, but that's actually giving me a value for my marginal distribution of x. All right, it's giving me the probability that x is equal to a. All right, let's do another example. So suppose I tell you x is a random variable. It's equally likely to take on any values from -1, 0, or 1. Y, however, is either going to be 1 if x is 0, or it'll be 0 otherwise. What is the joint probability mass function of x and y? take a minute, put it on pause. Why don't you try doing A and C? Or this should say function. All right, so joint probability table, let's think about this. I made the table to be -1, 0, and 1 for x's and 0 and 1 for y's because those were the only possible values. But now inside the table, I need to put the probability. So what is the probability that, let's say, x is equal to -1 and y is equal to 0? Okay, well, x is equal to -1 with probability 1/3. If x is equal to -1, let's see, I know that y will be 0 because that's the case here. So how am I going to think of the probability of this? Let's actually write out the possible values that x and y can be. So if x is -1, I know that y is 0. Well, x could only be -1 with probability 1/3, and then y is just following suit. So basically that probability is still just 1/3. Let's think about what's happening in this case. If x is 0, well then I know y has to be 1, and the only way that x can be 0 is probability 1/3. Y is just following its orders from x. Okay, so let's think through this. I actually think it's easiest to think through this by figuring out what are the possible combinations of x and y we can even have. So if x is -1, y is going to be 0. So that's one data point that I have, possible. If x is 0, I have that y is 1. And if x is 1, I have y is 0. I don't have any other possible combinations. So let's say that x was -1 and y is 1. There's probability 0 of that, right? Because y cannot be 1 if x is -1. So really the only non-zero probability combinations that I have for x and y are these three. And then I go to look and say, well, there's a third chance that x is -1, a third chance that x is 0, a third chance that x is 1. So this is actually completely defining. So these are the probabilities right here. And these are the possible combinations of x and y. Every other combination of x and y is going to have a probability of 0. So in terms of my table, I can write this as follows. I can say the probability x is -1 and y is 0 is 1/3. The probability that x is 0 and y is 1 is 1/3. The probability x is 1, y is 0 is 1/3. And every other probability, or a combination of x and y has probability 0. So again, this is an example of equally likely for every possible combination that I have non-zero probabilities for. So I draw my 3D histogram, and I can then think of this as a scatter plot if I'd prefer, because all three of these have the same probability. And then yes, I can also do a closed form function where I'm just saying the probability is 1/3, and those are the only three possible combinations. So this one again is kind of contrived, not as useful, but I like the idea of explaining this because we're going to look at these two random variables in a future lesson, and we're going to think about how this scatter plot, how the relationship on here is something that we're going to try to describe using a statistic. So that's why we've introduced this seemingly strange probability mass function. So far, I've only been looking at joint distributions with two different random variables. Oh, let's go back. All right, so now let's also calculate the marginal distribution for x and y here. So take a minute and do this, give your answer as a table. All right, so remember the marginal distribution, we're just adding here in the margins, these probabilities. So for x, I have a probability table 1/3, 1/3, 1/3. And for y, I have a probability table that says 2/3 and 1/3. And I can also picture these if I want visually. So here I have my scatter plot, but then I've actually shown a histogram of these marginal distributions on either side of the scatter plot. So you can see here's my uniform one for X, and then here's the 1/3, 2/3 for Y. So what if we do 3 random variables? So far we've just looked at 2 random variables and they're joined. All right, so now picturing this, I'm not going to be able to picture a histogram now because I'd need 4 dimensions. And if I give you this example of these 3 random variables, disease, smell, and fever, there's no closed form function that's explaining how these are related. So really my only option is a table. Really, I need a 3-dimensional table. I need a dimension for disease, a dimension for smell, a dimension for fever. And so the easiest way for me to show that on a 2D slide is just to break apart over one of the variables. So here's the table for D is 0, here's the table for D is 1. So altogether, the sum of this and these altogether now have to add up to 1. Again, this completely specifies everything I need to know about this joint distribution. So if I ask, for example, what's the probability D is equal to 1? Well, now I'm going to go look at all the possible ways D could be 1 and sum over all of the outcomes where D is 1. That's actually every outcome in this table, right? And that is how I could calculate the probability D was just 1. And that gets me, when you add it up, right around 5%. All right, so this seems, okay, kind of manageable. But what happens as we start to add even more random variables, right? So now think about, okay, suppose I have 10 discrete random variables, each of which can take on 5 values. Okay, so think of just what my column might look like for the first 2, X versus Y over here. I'm going to have 5 values here. I'm going to have 5 values here. But then I got to think about the next of those. I'm going to have 5 more there. I'm no longer going to be able to draw this in 3D. But I want you to realize is that just like when I had 2 random variables of 5 values each, I had 5 squared. If I have 3, I have 5 cubed. If I have 4, I have 5 to the 4th. And so this is going to be 5 to the 10th unique assignments that I would need, which ends up being approximately 10 million entries in your table. Okay, so this becomes quickly intractable from a logistical standpoint. Even if computers can, save these 10 million entries, I still have to have someone that's going out and collecting this information or writing in what is the probability for each of these 10 million different combinations. This becomes way too numerically problematic, right? And so we definitely, as you saw in WebMD, we definitely usually deal with more than just 2 random variables. But trying to do it by completely specifying the joint probability mass function is going to become a logistical nightmare. So this is where we need actual probability distributions that we can use as models. And I mean distributions that we can write a nice closed form function to describe their joint probabilities, something that's much more actually applicable and simpler that we can then apply to these more complicated situations. So in our upcoming video, we're going to introduce one such probability distribution called the multinomial distribution. So stay tuned.